Welcome back, everybody. Today we're doing a deep dive on a pretty important figure in AI, Vladimir Vapnik.
Oh yeah, definitely a big name.
We've got some excerpts from a site, it's like a bio site, about all these AI VIPs.
Okay.
Focusing on one article in particular. It's called Vladimir Vapnik, creator of support vector machines and AI pioneer.
Support vector machines, those are cool.
They are cool, and actually, even with all this deep learning stuff going on, his work is still super relevant today.
Yeah.
You've probably heard of support vector machines.
Yeah, for sure. It's hard to miss them.
So get ready, because we're going to learn even more about them.
I'm excited.
What I find really fascinating about Vapnik is that his work is rooted in, like, the theory of machine learning, the foundations.
Yeah.
And it still has a huge impact today, especially with all the hype around these massive deep learning models, right?
Absolutely. His work is, timeless in a way.
He is, yeah. Okay, so picture this. 1936, Soviet Union.
Okay.
Not exactly a place known for open scientific exchange, was it?
No, not really. Very much the opposite.
And this is where Vapnik is starting his career.
Wow.
Resources are scarce. Information's tightly controlled. What do you think that did to his approach to science?
I think it must have forced him to be resourceful and, incredibly rigorous.
Yeah.
Because he couldn't rely on just having tons of data or, these fancy computers.
Right, because they didn't have those back then.
Exactly. So he really had to develop this deep mathematical understanding of how learning actually works.
It's like if you can't brute force your way through a problem,
right?
You've got to get clever.
Exactly. You have to outsmart the problem.
And that's where his collaboration with Alexei Chervonenkis comes in.
Uh-huh.
Together, they developed this thing called the Vapnik-Chervonenkis theory.
Yeah, the VC theory, we call it.
Yeah, VC theory. And it tackles a really fundamental problem in machine learning. How do you train a model on a limited set of data and have it actually make good predictions on data it's never seen before?
Right, because otherwise, what's the point?
Yeah, that's what we call generalization, right?
Yeah, it's got to be able to generalize.
It has to. Because what good is a model that just memorizes the answers it's been given? It needs to handle new info, stuff it's never seen before, out there in the real world.
Exactly. It has to be able to adapt.
So VC theory introduces this idea of the VC dimension, right?
Right.
And it's this way to measure a model's complexity, like its flexibility to fit different patterns.
Like how well it can adapt to new data.
Yeah, exactly. Think of it like how wiggly a line you can draw to separate groups of data points. So the more complex the model is, the more it might overfit.
Right, exactly. Like it might just be memorizing the training data instead of actually understanding the underlying patterns.
Okay, so it's like you're trying to draw a line to separate cats and dogs.
Right.
Okay.
I like that.
A straight line, that might be too simple.
Yeah, it won't capture all the nuances.
But then a super squiggly line, that might just be memorizing the exact position of every cat and dog in your training data.
It wouldn't generalize well at all.
It wouldn't. And then when you bring in a new animal, you're like, what is this?
Exactly. It would be completely lost.
And that's where Vapnik's work on structural risk minimization comes in, right?
Right. It's about finding that sweet spot.
So it's all about balance. Finding that model that's complex enough to capture the patterns you want.
Yeah, the important patterns.
But not so complex that it overfits.
It was like a Goldilocks situation. Not too simple, not too complex.
Exactly, just right. So Vapnik helped figure out this balancing act.
Yeah.
But he didn't just stop at the theory. He actually helped create a whole new algorithm.
Support vector machines.
SVMs. These things take these principles and put them into action. What made them so important?
Well, I guess the key is that they find the best dividing line between two groups.
Okay.
But it's not just any line. It's the one that maximizes the margin.
The margin, what is that?
Yeah, so the margin is the space between the line and the closest data points from each group. So imagine you're drawing a line between cats and dogs, but instead of just drawing it right between them, you draw it so it's as far away from any cat or dog as possible.
Just like building a fence, right?
Yeah, like a fence.
But you're making the buffer zone as wide as possible.
Exactly. Just to be safe, right?
Right.
And this focus on maximizing the margin, it's directly linked to controlling that VC dimension we talked about. So a wider margin means the model is less likely to be tricked by random noise in the training data and more likely to generalize well.
Wait a minute, though. Real-world data, it's not always so neatly separated.
Right. You're right, it can get messy.
What about when you can't just draw a straight line to separate those cats and dogs? Like, what if some of the dogs are really small and some of the cats are huge? How do SVMs handle that?
Well, that's where the kernel trick comes in. This is where things get a bit, mind-bending.
Mind-bending. Okay, I'm ready.
So imagine you can't separate the cats and dogs with a straight line on a flat surface. But what if you could project them into a higher dimension, like lifting them into 3D space?
Okay, I'm picturing it.
Suddenly, you might find a plane that can perfectly separate them. That's the kernel trick.
Oh, that's pretty cool.
It finds a way to transform the data into a space where it becomes easier to separate. But the best part is it does this without actually having to calculate the whole transformation, which would take forever.
Oh, wow. So it's like a shortcut. So were you talking about like extra spatial dimensions here, like actual new dimensions?
Not literally,
Yeah.
but you can kind of think of it that way. It's like finding the best way to slice a cake so that everyone gets their favorite part, even if some people like the edges and some like the center. You might need to get creative with your cuts.
Okay, that's a delicious way to put it. So SVMs were a big deal because they could handle all that messy real-world data.
Exactly. And a lot of other algorithms at the time just couldn't do that.
So this theoretical power, it actually translated to real wins. Give me some examples. Where did all this lead?
Well, let's start with bioinformatics.
Okay.
SVMs were used to analyze gene expression. They were classifying proteins and even predicting diseases based on like all this complex biological data.
That makes sense.
Back in the early days of machine learning, this was a big deal because, labeled data was pretty scarce. And SVMs, they excelled in those situations.
Yeah. Bioinformatics often involves high-dimensional data and needs models that can actually learn from limited samples.
Right. And then there's finance.
Okay.
They were used for credit scoring, they were used for stock market prediction, even fraud detection. Basically, any field that needed to find patterns in complex data was turning to SVMs.
I bet they were used in image recognition too, right?
You got it. Object detection, face recognition, even recognizing handwritten digits, SVMs were all over it.
What about natural language processing, like analyzing text and speech? Could they handle that too?
Oh, for sure. SVMs have been used for things like text classification, figuring out if a piece of text is positive or negative, sentiment analysis, and even filtering out all that spam from our inboxes.
The range of applications is crazy. It's amazing how impactful all of this work has been. But it makes me wonder, how did Vapnik, with his love of theory, view this whole rise of deep learning? The data-driven experimental approach. Did he think this was a step backward?
That's the question, isn't it? And that's where we'll pick up next time.
Can't wait. Last time we were talking about Vapnik, right? This champion of like the theory behind machine learning.
Yeah, the guy really loved his theory.
But then deep learning came along, with its massive data sets and crazy computer power. So how did he feel about this new approach? Did he think it was a step backward?
Well, he definitely had some pretty strong opinions about deep learning. He wasn't shy about sharing them either.
Oh, I bet.
He saw it as lacking that solid theoretical grounding that statistical learning theory had, the theory he'd spent so much of his life developing.
I mean, I can see where he's coming from. If you need mountains of data and like supercomputers just to train a model, it makes you wonder if it's really learning the underlying patterns or just memorizing a gazillion examples.
And that's exactly it. He argued that deep learning was more like a black box, You get results, but you don't really understand why or how the model got to those results.
So no transparency.
Not really. And without that solid theoretical understanding, he was worried about its reliability in the long run. Like, could it actually generalize to truly new situations?
It's like a student who can ace a test by memorizing the answer key, but they can't actually solve new problems or apply the concepts to the real world.
Perfect analogy. And this goes back to the heart of statistical learning theory, understanding and controlling the capacity of models so they can actually generalize well.
Right.
Vapnik was concerned that deep learning with, its millions of parameters was just way too prone to overfitting, basically becoming too specialized to the training data and then failing when it saw new data.
So it sounds like he was a bit of a purist, right? Sticking to his theoretical guns, even as deep learning started to take over the AI world. But were these two approaches completely opposed? Was there any middle ground?
Well, it's actually a bit more nuanced than that. While Vapnik was definitely critical of deep learning, he also saw its potential.
Oh, interesting.
And what's really cool is that there's been some cross-pollination between his ideas and deep learning techniques.
Oh, so it wasn't a total standoff. Tell me more about this collaboration.
Well, one example is the use of regularization in neural networks. It's a technique used to prevent overfitting by penalizing complexity. And this idea really echoes Vapnik's work on controlling model capacity and finding that sweet spot between accuracy and generalization.
So even though deep learning models can be massive and complex, they're using techniques inspired by Vapnik's principles. It's like they're borrowing from his playbook to make their own models better.
Exactly, and it goes even further. Some neural networks are now incorporating margin-based optimization, which is directly inspired by how support vector machines work. They're taking cues from Vapnik's theoretical insights to improve their own performance.
That's amazing.
Oh.
It just goes to show that even though there are different approaches and philosophies in AI, there's still this recognition of valuable ideas no matter where they come from. It's not about one side winning or losing.
I completely agree. And it speaks to the fact that AI is constantly evolving. It's not about one approach dominating. It's more about finding ways to integrate the best of different worlds.
Now, speaking of Vapnik's contributions, I have to ask about his later work on learning using privileged information, or LUPI. It sounds like he was always looking for ways to make machine learning better, even while he was challenging the status quo.
Yeah, LUPI is a really fascinating example of how Vapnik drew inspiration from how humans learn. Think about it. When we learn, we often have extra information that helps us understand things better. Like a teacher might give us hints, or we might read explanations in a textbook. Things that wouldn't be available in a real-world testing situation.
So it's like having a cheat sheet during training that you can't use on the final exam.
Exactly. That's the core idea behind LUPI, to give the model this extra privileged information during training to help it generalize better, even though that information won't be available when it's making predictions in the real world.
Okay, can you give me a concrete example of how this might work?
Sure. Imagine you're training a model to diagnose diseases from medical images. The standard data would be the images themselves and the corresponding diagnoses, right? But with LUPI, you could also give the model extra information during training. Things like expert annotations on the images or detailed reports from biopsies.
Ah, I see. So it's like giving the model a more informed perspective during training, letting it learn from a richer set of information.
Precisely. And that extra layer of insight can help the model make more accurate and robust predictions when it's actually used in a real clinical setting where it won't have access to that privileged information.
This is really cool. It seems like Vapnik's work always comes back to this idea of improving generalization, making models that can truly learn and adapt beyond just the data they're given.
It really highlights his deep understanding of the challenges and nuances of machine learning, and his legacy continues to shape how we think about AI, even as the field is rapidly changing.
This deep dive has been so insightful. We've covered so much, from statistical learning theory to support vector machines, even Vapnik's critiques and later innovations. It's clear that his influence goes way beyond any specific algorithm or technique.
Absolutely. And his story is a great reminder that even in a field as dynamic as AI, those fundamental principles and theoretical understanding are always valuable.
But before we wrap up, I think we need to leave our listeners with a final, thought-provoking question to think about. After all, that's what a good deep dive is all about, right?
I agree. Let's give them something to ponder.
Okay, so we've spent this whole deep dive exploring the world of Vladimir Vapnik, a true pioneer in AI.
A legend, really. His journey from those theoretical foundations of statistical learning theory to his iconic support vector machines and all his later work.
It's pretty inspiring stuff.
Yeah.
But as we wrap up, what's that one big question that Vapnik's work really makes us think about?
I think it's this. In this age of data-driven AI, how do we balance all that raw power with a solid theoretical understanding? How do we find that sweet spot?
It's easy to get swept up in all the hype around deep learning with all its achievements, right?
Oh, yeah.
But Vapnik, he reminds us that there's so much value in understanding the why behind the how.
Definitely. His work challenges us to not just celebrate all those cool AI successes, but to really think about the limitations, the potential biases, to ask ourselves, are we building systems that are truly intelligent and reliable, or just really good at recognizing patterns?
Yeah, it's like, imagine building a bridge that seems to work perfectly fine. But if you don't understand the physics behind it, the engineering principles, you're always going to worry if it can handle unexpected stress, or changing conditions.
Perfect analogy. And that's where Vapnik's legacy comes in. He encourages us to keep asking those tough questions. Why do our models work? How can we make sure they handle new situations? What are the theoretical principles that make them successful in the first place?
Because at the end of the day, we want to build AI that's not just powerful, but also trustworthy and transparent.
Right.
Something that aligns with our values.
Exactly. And that takes more than just throwing tons of data at a problem and hoping for the best. It means we need to really understand how these systems work. We need to be willing to question their assumptions, and we need to build them in a way that is ethical and makes sense.
So whether you're building algorithms using AI in the real world or just fascinated by all the possibilities out there, remember what we can learn from Vapnik's journey.
Absolutely.
Embrace the power of all this data, but don't forget about the theory.
The theory is key.
Try to understand not just what works, but why it works.
Yeah, the why is important.
And don't be afraid to challenge what everyone else is doing. Push the boundaries of what's possible while still being grounded in those solid principles.
I think that's how we build an AI future that's not just impressive, but also meaningful. Something that actually benefits us and that we can actually trust.
Well said. Thanks for joining us for this deep dive. Until next time.
That's been fun.